Okay, moving on to the third one, and this time we're going to see if we can use our acquired skills for determining the equation of an exponential function, y equals b times a to the x plus q. And again, they're just playing around with different variables there, not so that they can be difficult, but just to emphasize that those letters can be anything. And in fact, in the example, they switch it and they say the graph of y is equal to p times q to the x plus t is sketched below. And they would like us to determine the values for p, q, and t. So I can see you saying, oh, that's 3 variables. What on earth am I going to do? But just keep your wits about you, and let's see if we can apply them step by step. So yes, I've got an exponential graph. It's actually an increasing exponential graph. Okay, so what do I know? I definitely know, before I start, that my q value is going to be greater than 1. Okay, remember, exponential increasing happened when my q value was greater than 1. What do we know about the plus t? Guys, we know that the plus t is what has actually taken the normal graph and shifted it up or down. Now, do you recall that your normal graph looked something like that, and it had an asymptote with the x-axis, or the line y equals 0. Now, you can see that what's happened here is that this graph has actually just dropped down by 3 units in total, down to -3. And the only way that we could have done that is the effect of this parameter at the back here, this t value. So I can immediately turn around and say, right, if you are wanting the equation p times q to the x plus t to match the picture, then I already know that my t value has to affect a change of dropping the graph down by 3, so it's going to have to be -3. Okay, so I'm sure that you are in agreement there. Now we've got something which is a little bit different to before. Can you see that I'm left with a p, a q, and a y? But what did we do before, guys? We found a point that the graph goes through. So let's just kind of do that again. Just do what we know worked for us before. So I'm going to use a point which is quite clear to me. This one here at the origin, I'm going to use the point 0, 0. And see what happens when I plug that in. So the y value is 0, is going to equal p times the q to the power of 0, injecting the x value as a 0, subtract 3. And why that works so beautifully is because we know, once again, exponent laws coming through, that q to the power of 0, all right, is equal to 1. So, in fact, we've got p times 1 subtract 3. Okay, now you can see that we are just a step away from finding the true value of the mystery letter p, because we can now see that p times 1 is p, and if we just transpose this to the other side, we get p to be 3. Are we done? Definitely not, because we've now got the t value. Given its identity, we've got the p value, but we are now still looking for the q. So let's have a look at what our equation has become so far. We now know that it's y is equal to 3 times q to the x minus 3. So now we scratch our head and we say, well, what do we do now? We've never had this circumstance before. Well, I think what we're going to do is we're going to have to use another point to try and work out what that missing value is. So let's have a look at what we could actually find on the graph. Now, for me, I think that the best point for me to use would be this one here, which is 1 across and 3 up. Okay, now clearly, if they gave this to you in a test, it would have to be really drawn accurately to scale. They can't have you guessing what those coordinates are. So I can see that that's 1 and 3. So that's the point that I'm going to use to finally try and get my last mystery variable. So plugging that in, I now have 3 is equal to 3. The q is still there, but my x value is a 1. Subtract 3. And just working that out ever so quickly, I've got 3. This is going to become a plus 3 when it comes over onto the left-hand side. And q to the 1 is obviously just plain q. So 6 is equal to 3q. And so finally, my q value gets its definition, and it becomes q is equal to 2. So what is the final equation? Well, it was 3, the value I found for p, times 2, the value I found for q in this final step, times to the exponent x, subtract 3. And if you really want to be perfect, we can put that 2 into brackets to indicate, of course, that the x only works with the 2, so that you do not think in error that that's a 6 to the x, but it is only a 2 to the x multiplied by 3, then dropped down by 3 units. So can you see that in these 3 examples, what we've actually done is we've found a method that allows us to find the equation of any graph that they give us. We saw that with the parabola, we just had to find out how much it had been lifted, then sub in a point. Then with the hyperbola, we found out how much that asymptote had been lifted, then we subbed in a point. And then repetitively, we had to find out how much had this asymptote been dropped. We saw that that had been dropped down by 3 units. And then because we had 2 further variables to find, we had to not only sub in 1 point, but another one as well. And just to finish off, we could have used any other point as long as we could have read it off accurately enough for us to inject it into the actual equation. Right, grade 10s, we've come to the end of this lesson on functions. If you've watched it in its full entirety from beginning to end, I'm sure you're going to need a medal. I'm sure you feel quite exhausted. It's been really a very, very laden with concepts type of lesson. So really what I would like you to do is to rewind and replay it in bits and pieces, because we've looked at drawing graphs, we've looked at the effect of A, looked at the effect of Q, and in addition what we've done is we've taken a graph which was a complete mystery, and we've then been able to assign its defining equation. Lots and lots of concepts to actually get into your brain at one go. So well done, and thank you for staying with me.